Hello, everyone, and welcome to the Toronto Geometry Colloquium. This is a weekly web series all about geometry processing.
This colloquium aims at promoting young researchers and researchers from traditionally underrepresented communities.
And every week, we'll have an opener talking about their cutting-edge research for 10 minutes, followed by a headliner giving us a keynote presentation.
And today, we are thrilled to have Yifei Li as our opener to talk about differentiable cost simulation, and Joshuah Wolper to talk about particle-based simulation. A reminder, if you have any questions for the speakers as they do their presentation, you can write them in the YouTube live chat that we'll be monitoring them. And we will be asking those questions at the end of the talks. If you ask the questions when you have them, it helps us curate a better Q&A. So don't wait until the end of the talk to ask your question. Our first speaker today is Yifei Li, a PhD student at MIT. In the past, she has worked at Google, Meta, and Activision Blizzard, and got her bachelor's degree from Carnegie Mellon University. She is an MIT Presidential Fellow, and her work focuses on simulation and computational design. I'm really excited that she's joining us here today to talk about her fascinating work on class simulation. This is really, if I may editorialize, it's one of these papers where you can just stare at the animations for hours and hours on end. So like one of the very fun to watch SIGGRAPH papers. So I'm really excited that we host her today. You can take it away now, Yifei.
Okay, thanks Sylvia for the introduction. Let me share my screen. So today I'll present our recent work on differentiable class simulation with dry fictional contact. This is a joint work with Tao Du, Kui Wu, Jie and Wojciech Maciusek. Class is everywhere in our daily life, and class simulation has wide applications in many areas. Film and game industry use class simulation to create beautiful animations and visual effects. Fashion designers use it to prototype garments. Roboticists use it to develop robots that assist people to dress, and consumers use it to try on clothes virtually while comfortably staying at. Many of these applications share in common that they need to repeatedly use simulation to achieve some desired goals. Consider the task of garment prototyping. A typical workflow involves the designer to make small changes to the design, then verify the design using simulation. This process is repeated many times until the design is finalized. There are a few issues with this workflow. First of all, simulating class is challenging because it has large degrees of freedom and frequent contact and collision events. As a result, accurate simulation comes at a cost of long simulation time. Second, iteratively manual editing is tedious. It would be great to have a computational workflow to assist the process. This is where differentiable simulation can come into play. Imagine you need to perform a task, say tweaking the material settings of a dress so that the dress spins like a ballerina dress. With differentiable simulation, we can first simulate the class through time with an initial parameter set, then measure how far we are from our goal using loss function defined on the parameter. Because the computation process is differentiable, we can reverse the computational order and derive the gradient of the loss with respect to the parameter. This gradient information allows us to then use gradient-based optimizer to update the parameter. We can iterate this process until we find the parameter that minimizes the loss. The closest to our work is that of Liang and colleagues, which presents a differentiable class simulator. However, the proposed framework uses a non-physics-based contact model. Furthermore, the simulation framework uses Newton's method and directly performs backpropagation using Agile method, making the whole framework very slow. The full simulation models in our differentiable simulation framework uses the work proposed by Li and colleagues, which presents a projective dynamics-based simulator that supports dry fictional contact. Lastly, Du and colleagues presents a fast PD-based soft-body differentiable simulator, which directly inspired our work. However, comparing to our method, the framework is limited in the types of contact events it can model. In this work, We present DiffClass, a differentiable class simulator that is RAS, models dry frictional contact, and has demonstrated effectiveness in various inverse tasks. Its performance comes from projective dynamics-based forward simulation and a novel gradient computation trick to speed up backpropagation. We demonstrate the effectiveness of the simulator in tasks including system identification, inverse design, trajectory optimization, closed loop control, and real-to-sim tasks. To simulate class in time, implicit time integration over Newton's second law is used for simulation stability. After time discretization, it involves solving a nonlinear equation over the net state of class at t+1. Traditionally, it is solved with Newton's method, which is very slow because each step of the simulation requires a costly system matrix calculation and factorization computation. This poses a problem in differentiable simulation because during backpropagation, we need to solve a linear system with this matrix. This leaves us with two options. Either we recompute and refactorize the matrix for each backpropagation step, which will be very slow, or we store the factorized matrix in all time steps, which requires lots of memory. Lots of research effort has went into speeding up forward simulation from the graphics community. In particular, in projective dynamics, by assuming the energies of the simulation take certain forms, the system matrix ends up the same across the whole simulation. This means in all time steps, only one matrix needs to be computed and factorized, significantly speeding up the forward simulation. With some algebraic tricks, we can let backpropagation solve a linear system with the same system matrix. After contact gradient computation, DiffClass applies this speed-up trick to projective dynamics with gravitational contact. We now end up solving linear systems with the same system matrix in both forward simulation and backpropagation, making the differentiable simulation framework extremely fast. To see how DiffClass compare with gradient-free methods in solving inverse tasks, we designed this benchmark inverse problem that aims to optimize force field on the class to reach a ring at the end of the simulation. We solved the task with gradient-based optimization using DiffClass and gradient-free methods, and see that in our gradient-based methods is hundreds-fold more efficient than the gradient-free counterpart. We repeated the task with different numbers of design parameters and see that the advantage becomes more obvious as more optimization parameters are involved in the task. Many class-related applications can benefit from a differentiable simulator. In the system identification task, DiffClass is used to identify the wind model parameters and closed throw parameters from a motion trajectory. After a few iterations of optimization, the motion trajectory successfully matches the target trajectory. In this trajectory optimization task, we seek to optimize the motion trajectory of two end effectors hanging on the hat. The goal is to move the hat onto a head model. In our experiments, the task can successfully be completed with various initial trajectories. Here, we demonstrated a similar task that seeks to optimize the motion trajectory of four end effectors hanging on a sock. The goal is to move the sock onto the foot model. This is a difficult task that shows frequent contact events between the foot and the sock model. And again, our gradient-based optimization can solve this task with very few optimization iterations. Inverse design of garments is another area that can benefit from differentiable simulation. In this task, we aim to optimize the dress material parameters so that after spinning, the bottom of the dress reaches certain heights. The task involves a large simulation that highlights frequent self-collision events. Our experiments show that gradient information can still be very helpful even under this situation. Our differentiable simulator can naturally be integrated with machine learning frameworks. To highlight this ability, we demonstrate an advanced head task that trains a closed-loop controller using a neural network. The goal of the controller is to move the head onto the head from any starting positions around the head. The trained controller takes as input the state of the current head mesh and end effector positions, and outputs an action that says how the end effectors should move in the next step. Thanks to the gradient information provided by DiffClass, we're able to train this controller in a very simple, efficient way. Compared to reinforcement learning, which is a gradient-free learning method, our gradient-based optimization uses 85 times less simulation iterations to finish the training. To summarize, in this work, we present a differentiable class simulator that models dry frictional contact. DiffClass is very fast because it uses projective dynamics for its forward simulation and adds the efficiency in forward simulation to speed up backpropagation of gradients. The effectiveness of DiffClass is demonstrated in a wide range of inverse tasks. We observe significantly more sampling efficiency to solve this task using our gradient-based optimization methods compared with gradient-free methods. With that, I'll end my presentation. Feel free to let me know if you have any questions about DiffClass, and thank you for listening.
Thank you very much, Yifei. That was an amazing presentation. That sock example was incredibly good. Thank you. If you could stop sharing your screen now, we can. Yeah, great. All right, so as usual, we will now move to our headliners talk, and we'll have a joint Q&A with both at the end. So make sure to leave your questions for Yifei in the YouTube live chat. Our headliner today is Joshuah Wolper. Dr. Wolper got his PhD at the University of Pennsylvania, where he is now a postdoctoral researcher. He's nothing short of a personal and professional inspiration for me, and this makes me particularly honored that we get to host him today. His work on the material point method, which we have featured before in our colloquium, produces some of the most impressive animations I have ever seen, and I think you have ever seen. And I hope we get to see some of those today. He's also a positive example of how PhDs are not just about specializing in one single area. At times it can seem like it, but rather about getting many transferable skills that he's now applying in his postdoc in what to many of us seems like a completely different field. So I also hope that we get to hear about some of this today. Anyway, I won't take more of your time. You can go ahead, Dr. Joshuah Wolper.
Yeah, thank you so much for that wonderful introduction. Oh my gosh, I'm so honored to be here. This initiative y'all have put together is just incredible. So let me bring this up. So yeah, thanks again for having me today. I think it's just so wonderful. You're making all of this exciting research so accessible. And yeah, I'm just honored to be here. So I have a lot to get through, so let's jump into it. So in my PhD thesis work, I worked on methods for simulating material fracture, and this was mostly in the context of computer graphics to animate dynamically fracturing scenes. However, many of these methods actually do have their origins in engineering, and during my PhD, I had the exciting opportunity to also collaborate with a multidisciplinary team of snow and ice scientists to apply these methods to the real-world scenario of glacial calving and tsunami generation. And this real-world application was so exciting to me that when I finished my PhD last May, I jumped at the chance to take on a postdoc in exploring biological fracture towards the simulation of life-threatening thrombotic embolism. So for this talk, I'll begin with an overview of my experience in simulating material fracture for graphics, and then transition into looking at this problem of fracture simulation through the lens of engineering, where accuracy and validation techniques become much more crucial. So let's start super low level. Why do we care so much about fracture? Well, it surrounds us every day, whether we're chopping vegetables or dropping something on the ground, but it's a notoriously difficult phenomenon to understand, let alone to simulate in an elegant and robust way. And as you can imagine, modeling fracture has applications in just about everything, from animated movies to interactive mediums like video games. And of course, fracture modeling really has its roots in the fields of mechanical and civil engineering to make our lives as safe as possible. And naturally, each application of fracture modeling has different ideas about what successful fracture modeling should achieve, because we can't achieve it all at the same time yet. So real-time applications such as video games strongly favor speed over accuracy and often avoid fracture physics entirely, while offline simulation for movies and VFX focuses on artistic control and the look of fracture rather than accuracy. And lastly, engineering applications were the first to inspire the study of the physics behind fracture due to a need for predictive accuracy rather than speed or look. And finally, I want to give you some intuition about what pieces we need for successful fracture modeling. So the first is some governing physical theory that describes how cracks begin and how they grow. The second is a way to discretize material geometry and the underlying partial differential equations that govern fracture. And lastly, we need a way to track and represent the growing crack front, which can be tricky due to the extreme topology change and evolving discontinuities that are intrinsic to fracture. So how should we simulate fracture? And more specifically, how should we discretize our material if it's going to be dramatically changing topologies over time? Well, the most common approach so far is to take a meshed approach where the material or crack surface is triangulated into a nodal mesh that we can integrate over. More specifically, the finite element method and boundary element method have both been put to great use simulating fracture over the years. However, meshed methods do have difficulty with two elements of dynamic fracture. So modeling extremely large deformations can cause unwieldy mesh entanglement, and the intrinsic material separation itself requires clever treatments to remesh every single time the topology changes, and this can grow to be expensive. So as an answer to some of these difficulties, meshless approaches have also been explored in which the material is discretized as a discrete set of particles filling the material volume. However, these meshless techniques often struggle with a different problem, which is in representing strong material discontinuities. So for example, here, CPIC on the right avoids fracture physics entirely and instead directly geometrically partitions the material. As for today, we'll be focusing on using our understanding of fracture physics to augment a meshless simulation approach called the material point method. So what's so special about MPM and why use particles at all? Well, first and foremost, MPM uses what's known as an updated Lagrangian formulation, meaning that it measures deformations as changes between individual time steps. And this means that the deformation gradient we use in MPM is an approximation of total Lagrangian deformation. And this allows MPM to robustly handle extremely large deformations and topological changes, making it ideal for both solids and fluids, as well as elastoplastically flowing materials like snow and sand. Second, MPM can handle many different materials at once and has intrinsic collision handling such that MPM materials naturally resist interpenetration for free, whereas in FEM these collisions might be handled with many different penetration checks on the updated meshes. And third, MPM research has quickly amassed a breadth of successful physical effects in materials, including snow, sand, sediment flow, continuum foams, melting, phase change, baking, and of course, fracture. And finally, one of the most exciting things about MPM to me is the physical accuracy of the method, making it not only successful for producing these beautiful physically based animations, but also extremely useful in real-world simulation and scientific computing. So for example, in predicting gravitational hazards like avalanches, landslides, and tsunamis. So for the rest of this talk, we'll be looking at the ups and downs of simulating fracture using particles through the material point method. We'll begin with an overview of the continuum damage mechanics approach to simulating fracture with MPM, and we'll discuss the engineering concepts of CDM and phase field fracture to see how they can be used in computer graphics. And then we'll look at how we can animate fracture using plasticity, which is just a completely different physical approach from phase field fracture. And here we'll also discuss how we can take this computer graphics work and apply it to the real world scenario of glacial capping and tsunami generation. And this will also introduce our discussion of accuracy and validation methods. And finally, the brunt of this talk will be a discussion of my current postdoc research in simulating the fracture of blood clots. So here we'll have a third act twist and look at just how well MPM can handle classic scenarios from fracture mechanics. And based on this, we'll also discuss how we can make MPM fracture tremendously better using a two-field scheme. So now before diving in, let's quickly overview the MPM algorithm a bit. So MPM discretizes a material both as a set of particles and as a grid of nodes. It uses the particles to keep track of data like the velocity and position, while the grid nodes are used as a scratch pad for spatial derivative computations. The core loop of MPM entails transferring data from the particle view to the grid view, and then using the grid to perform force computations and update velocities. Then the updated velocities are transferred back to the particles and used to advect particle positions. And then this loop repeats for each step of simulation. And in this figure here, the green boxes indicate particle views while the yellow boxes show the grid view. So we begin at the top left where we have our particle positions, masses, and velocities. So step one is to transfer our mass and momentum to the grid using our interpolation routine. So labeled 1, we see the grid mass and momentum. Next, in step 2, we calculate the external and internal forces on the body so that in step 3, we can time step the velocities on the grid. And internal elasticity is usually modeled using a constitutive model that gives us a relationship between the deformation and the material's energy density. And then after we update velocity on the grid, we transfer this velocity back to the particles in step 8. And then in step 9, we use velocity to advect particle positions. And the really cool thing here is that to augment MPM with effects like melting or fracture, we can introduce new data to the particle view like temperature or material damage, transfer this to the grid, and then use the grid to update these properties by solving the corresponding PDEs before transferring them back to the particles. And this transfer back and forth between particles and grid nodes will be very important later, so we'll come back to that. And finally, steps 4 to 7 deal with handling plasticity, so we'll discuss this in a bit too. Next, let's go over a brief introduction to continuum damage mechanics and phase field fracture. So continuum damage mechanics uses a smeared crack approach, also known as diffuse crack modeling, which assumes that the material remains a continuum, and instead the mechanical properties of the material are weakened at the cracks to account for the effects of fracture. And within CDM, damage can be modeled either locally, such as through comparing local stresses with some defined maximal stress, or non-locally through tracking a scalar field of damage variables evolving over time. And this latter approach is known as phase field fracture, or PFF. So for PFF MPM, we can augment traditional MPM with phase field fracture through tracking damage in the particle view and evolving damage variables on the grid, which then in turn affect the force computations. And these phase values are constrained to be between 0 and 1, with 0 being healthy material and 1 being fully damaged material. So in the image at right, the disk is considered to be a continuum in material space at left, but the phase is tracked such that in the high damage red region, we see material separation at right because the material has been weakened at the crack. And the damage variables that we track and evolve influence the material's elastic response through a method of elastodamage coupling known as elasticity degradation. In this context, we achieve this by multiplying a monotonic degradation function G that's based on the current damage. And below you can see this degradation function to show how it smoothly transitions from 1 to 0 as damage increases from 0 to 1. So now let's really quickly take a look at the data flow of PFF-MPM. So the key difference from traditional MPM is that we now additionally track damage or phase per particle and perform a similar set of steps to transfer, solve, and update these phase values. That's that second column. And these arrows here show our staggered integration approach for this. The blue arrow shows that we use the particle's current deformation gradient in the phase solve on the grid. And then once the phase is solved and transferred back, the red arrow shows that we use the updated particle phase in the force computation to ensure that we've updated the damage before we compute forces with elasticity degradation. So let's take a quick look at some of the effects we can achieve with PFF-MPM. So here, when we shoot this Jello T-Rex with a bullet using traditional MPM, the fracture pattern's at the mercy of unpredictable numerical fracture, which is a unique type of MPM fracture that occurs when material is forced to tear non-physically. And we'll actually discuss numerical fracture more later because it's going to become important. However, using PFF-MPM, we get the desired trajectory through the T-Rex. And here we again visualize the phase field to show crack formation and propagation. Similarly to before, we twist a Jello bar with traditional MPM to show that in some cases, numerical fracture can't produce the desired behavior, let alone any fracture at all. And fortunately, with PFF-MPM, we achieve the desired fracture pattern as the Jello twists. And finally, we slowly tear a piece of bread to reveal the intricate fracture patterns and dynamics we associate with fresh bread. And we again visualize the phase field to show off all the small fractures invisible in the render view. So with PFF-MPM, we produced a breadth of isotropic fractures, but many materials are actually anisotropic and have underlying fiber structures that give them different directional properties. So let's go over the companion piece to PFF-MPM and iso-MPM. But first, let's go over just some terminology. So isotropic materials behave the same in every direction, like a jiggling Jello cube. Transversely, isotropic materials have one direction that's stronger than the others, like our muscles. And finally, orthotropic materials can have different responses in every direction, with the most intuitive example being wood, with its axial, radial, and circumferential directions. So for brevity, we can think of aniso-MPM as being very similar to PFF-MPM with the addition of two ingredients. The first is the incorporation of structural tensors that allow us to encode the material anisotropy. These tensors go into a crack driving state function d tilde that we visualize here on the right. And notice here how this function responds differently to stresses in each direction depending on the fiber orientation, especially compared to the far right isotropic case that behaves identically in every direction. So the second crucial ingredient here is the addition of anisotropic elasticity. And to visualize this, we stretch 3 anisotropically elastic tubes and display their cross sections. So notice here that the isotropic tube contracts the same in every direction. The transversely isotropic tube shows less compression in the principal fiber direction. And finally, the orthotropic material shows that we can further scale the secondary fiber direction for less compression in that axis. So now let's quickly see what kind of fracture animation we can achieve with aniso-NPM. First, we want to peel apart the layers of a piece of Dongpo pork belly using different anisotropic settings. So first here we try isotropy, but clearly this only allowed us to tear a small piece away. And next we add flat diagonal fibers to enable transverse isotropy. And so now we're at least able to peel away a strip of the meat. And finally, we add a secondary fiber direction to model orthotropy and can now peel apart the individual layers. And we also color the particle damage in the top right to visualize the evolving planar crack. So next, this transversely isotropic string cheese is pulled in 8 directions to partially peel apart the stringy fibers intrinsic to a pulled cheese like mozzarella. And lastly, this orange is simulated with radial fibers, each exhibiting local transverse isotropy. And here we again show the damage. So now that we've taken a really quick look at damage-based NPM fracture animation, let's jump into discussing plasticity and validation. So let's start with some background on plasticity. When simulating plasticity, we typically do a multiplicative decomposition of the deformation gradient into its elastic and plastic parts, seen through the progressive deformation of the bread at the right here. And we also need to choose a yield surface, which is effectively a 3D boundary and principal stress space that separates stresses into those that cause elastic deformations and those that cause plastic deformations. And at right is a 2D slice of the Drucker-Prager yield surface cone in Kirchhoff's stress space to illustrate this. So points inside this surface represent stresses that cause elastic recoverable deformations, whereas stresses outside cause plastic irreversible deformations. And with a yield surface in hand, we can develop a return mapping routine that involves using the elastic deformation to determine where in stress space a particle is, and then, if necessary, projecting it back to a feasible stress state. And based on this projection, we also update a hardening variable per particle to keep track of the plastic deformation over time. Ultimately, this influences the shape of the yield surface for each particle, capturing the plastic softening or hardening of the material. So to simulate material fracture with plasticity, we begin with the cohesive cam clay yield surface used by Gohm et al. In 2018 to accurately model and predict avalanche mechanics. And the key difference here for our fracture scheme is that we choose a non-associated flow rule, meaning that we project our stresses orthogonally to the hydrostatic axis, which is the x-axis in the chart here. And you can see here that we have 3 cases for return mapping. And the big takeaway is that in cases 1 and 2, we have a clearly defined change in pressure, delta P, that we can use to update the volumetric plastic strain. However, in case 3, since we project orthogonally to the pressure axis, we have no change in pressure, only a change in the deviatoric stress variant Q. So to accommodate this, we instead used a geometric intersection problem to compute an approximate change in pressure that we can then use to approximate the volumetric plastic strain log JP. And this is a simple trick that works quite well for graphics, but would be a much harder sell to an engineering audience. So now let's quickly see what kinds of fracture we can animate with NACC plasticity. So here we see a showcase of NACC plastic fracture animation, demonstrating that its best use is in animating huge debris-laden fractures like these. In the top row, also notice that we visualize the particle hardening values for the pumpkin and the crab in material space to visualize where the material has plastically softened enough for a separation. So while we saw that NACC plasticity has exciting applications in VFX, we also found that we could make it even more physically accurate for the purposes of modeling real-world scenarios like glacial calving. So here we see a large piece of glacial ice calving off into the ocean with an enormous splash and ensuing waves. And modeling this glacial calving is not only pertinent right now due to the inevitable sea level change due to global warming, but also because these types of calving events can cause fatal tsunamis that could dramatically affect coastal regions. So let's see how we can model this by making NACC plasticity even more accurate. So we just saw that due to our non-associated flow rule, we have this tricky isobaric return mapping for case 3, and we solved this through that non-physical intersection problem. However, we do have a change in Q, delta Q at the left. So we sought out a way to develop a Q hardening approach for case 3. More specifically, we're inspired by the quadratic relationship between P and J and designed a similar relationship between Q and a new J-like quantity zeta. And this is just a constitutive modeling trick that we can employ to more accurately capture the unique dynamics of different materials. But you might feel at first that this is just trading one non-physical approximation for another. So here we'll start discussing these types of simulations in terms of how we can validate them. So first, since glacial calving is a process that happens on a very large scale, we can look at pretty large scale validation approaches. Here we show the progression of a 2D simulation of a glacier calving into water with the height marked H, the submerged depth marked D, and the fractured iceberg length marked L. Also notice that we color the water based on velocity, with blue being 0 meters per second and red being 20 meters per second, while we color the glacier based on the hardening alpha like before. And at the top right, we show an analytic bending expression that we developed from beam theory to validate the iceberg lengths from our simulation. And as you can see in this chart, our 2D calving simulations follow this analytic model very nicely. And we even see that when we reach around 0.92 on the x-axis, which is the ratio between the density of ice and water, we see that the glacier no longer fractures at all due to being fully supported by buoyancy. And now we can move on to a real-world example. So here we simulate in 2D the Ikip-Sirmia Glacier in Greenland. And as you can see, we've modeled the ice crevices of the glacier using Perlin noise, as well as approximately matching the fjord depth. And excitingly, with the assistance of some 2D to 3D transforms, we found that this simulation quantitatively agrees with a variety of mechanical properties from this real-world calving event. And some of these exciting results include the wave amplitude, the average wave speed, the angle of the failure plane, and the width of the failed portion. So ultimately, we've shown that NACC plasticity paired with our new Q hardening approach has the potential to be used to predict these types of dangerous tsunamigenic glacial calving events. And we also simulated a wider glacier here using 36 million particles to focus on the ice fracture characteristics. I'll show this for a little bit. And then here we've rendered the scene as if we were viewing this event from a nearby boat moving with the waves. So you can also see the underwater view of the fractured icebergs. So now let's finally get to this twist. So let's jump into our discussion of my current postdoc research into simulating the fracture of blood clots. So let's start by looking closely at this problem we're trying to solve here. Our blood naturally contains a protein called fibrinogen, and when we get a cut, fibrinogen is converted into fibrin, which serves as a mechanical scaffold for entangling platelets and forming a wound-healing blood clot. However, fibrin clots also naturally build up in the circulatory system over many years. And these clots naturally have imperfections, and these places of material weakness are further weakened over time by enzymes in the blood and the constant shear effects of blood flow. So this continues until the clot fractures, forming a life-threatening thrombus that can travel downstream and block vital blood flow to the brain or heart, causing thrombotic embolism that causes a stroke or heart attack. So obviously, this is a life-threatening biological mechanism that affects us all. So we want to understand more about the material strength of these fibrin clots and how we might be able to predict or prevent them from happening at all. So we need to capture this complex multi-material phenomenon with as much accuracy as we can. So let's go over what ingredients we need to simulate this. So first, we need highly accurate constitutive models that describe the relationship between stress and strain for the three core materials involved here. Artery walls are composed of anisotropically arranged tissue layers. The fibrin clot itself behaves like a porous hydrogel, and the surrounding blood flow has viscous fluid effects, meaning that these three materials need to be treated quite differently from one another. And second, we need a simulation framework that allows us to capture many of these intrinsic effects of these materials on their own, but also when they interact. So specifically, we need a framework that can handle multiple complex materials in their natural collisions, handle very large material deformations since we're working with soft materials, and handle extreme topology changes since we're trying to capture fracture. And since we're focusing on a developing crack in our core material, we also need to make sure that our framework is capturing accurate fracture mechanics near and inside this crack. So NPM on paper sounds like the perfect match for this problem, right? It's known for success in modeling the first three metrics here. But for this real-world context, we need extremely good accuracy and rigorous validation to ensure that this method is capturing accurate fracture mechanics near the crack. So let's take a look at how we can validate MPM's performance on the fracture mechanics side. In particular, today, let's look at the treatment of free surfaces that are in or nearly in contact. So to do this, let's take a look at a classic loading scenario from fracture mechanics, the single edge notch tension test. This scent test simply puts a crack of length A in the left side of a specimen and then quasi-statically loads the specimen in the up and down directions to put it in tension. In the MPM framework we've discussed so far, we can model this as a region of high damage where we want the crack to be, and then we can simply load the top and bottom with some applied stress, sigma applied. And let's also use a simple tensile elasticity degradation to weaken the material in the damaged region. So this elastodamage coupling simply uses the particle damage D to degrade the tensile portions of the material stress, meaning that fully damaged particles should be able to physically separate under tension. Then one of the simplest validation tests we can do on this specimen is simply to measure the traction at the crack surface. In particular, because we're loading this crack with tension up and down, the crack surface on the top and bottom should be traction-free, showing nearly zero stress in the up and down directions. So let's take a look at how MPM performs on this simple validation test. So here we're looking at the particles along the top edge of the crack, and we plot the stress concentration factor, sigma 22 over sigma applied, against the proportional distance from the crack opening the particle is. So each data point is the stress concentration factor at a particle along the top edge going from left to right. And by now you've probably noticed that this stress concentration factor is quite far from the zero that we want to see here along the crack surface. So what's going on here, and how could MPM produce all these beautiful animations but be so directly struggling with modeling a traction-free crack surface? Well, to explain this, let's take a closer look at MPM's interpolation routines. So recall that in MPM, we interpolate our particle data to the nearby background grid nodes, solve our dynamics over the grid's degrees of freedom, and then transfer updated quantities back from the grid nodes to the particles. So for example, here we have the expression for grid node I's momentum as the sum over all particle momentums in some influence region, each weighted by some interpolation weight Ni. And it's this weight that's crucial here. MPM interpolation uses a dyadic product of 1D B-spline interpolation functions to map between particles and grid nodes. And this function is typically quadratic or cubic, but for this talk, we'll focus on the quadratic. And most importantly, to transfer particle data to the grid, we iterate over each particle and find a base node that defines the 3x3 kernel of influence of this quadratic interpolation function, and then transfer data to the nodes in this 3x3 stencil of nodes. And this interpolation is fantastic for the most part, preserving mass and momentum and other properties as they go back and forth between particle and grid representations. However, we run into a big problem when we want to represent a strong material discontinuity like in our scent test. So we see here a close-up render of the damaged particles that defined the crack. So let's mark two particles, one above the crack and one below. When we visualize the interpolation stencils here, the problem becomes immediately more clear. The particle above the crack is interpolating an upward velocity to its nodes, and the particle below the crack is interpolating a downward velocity. So this is effectively smearing out this strongly discontinuous velocity field, and ultimately we get a non-zero traction here along the crack surface. So with this issue in mind, how did we accomplish all of these damage-based fracture animations? Well, first and foremost, it's important to emphasize that phase field fracture theory does regularize the diffuse crack fields, and we can set this regularization parameter to be in terms of the grid resolution to ensure that the crack region is within a single grid cell, for example. But this isn't solving MPM's struggle to capture strongly discontinuous velocity fields. So existing damage-based fracture approaches are not directly modeling traction-free crack surfaces, but instead are actually using damage to drive something in MPM we call numerical fracture. And numerical fracture is simple. When continuous regions of particles get stretched too far apart, they're no longer mapping to the same grid nodes, and we get a non-physical fracture as these particles' interpolation stencils move further apart and their interaction forces drop to zero. So as you can see, if we pull hard enough, we get this effect without modeling any damage at all. And counterintuitively, higher grid resolutions will actually be more prone to numerical fracture, as you can see here, because it's easier for them to move too far apart. So when we pull the arms off of this armadillo with PFF-MPM, the damage is evolving accurately and accumulating near natural fracture points. But as we just saw, this damage region is not necessarily accurately capturing a traction-free surface. And instead, the fracture that occurs is a damage-driven numerical fracture. So ultimately, traditional single field MPM isn't fit for highly accurate fracture simulation, but we still want to find a way to maintain all of the great benefits of MPM while solving this really tricky issue of strong discontinuity. So specifically, we need to enable MPM to more accurately capture surfaces in contact and the associated contact forces and friction. So aside from the cracked surfaces case, we can also look at this simple free surface interface between this block and the slope it's trying to slide down. So here, MPM's interpolation routines are blending this sharply discontinuous velocity at this contact interface, preventing the real contact we want. So to solve this, we're inspired by two-field MPM, a method put out by Homel and Herbold at Los Alamos National Labs in 2016 that's quickly gained some traction. So let's quickly go over this approach. In two-field MPM, each grid node can be partitioned into two fields that are in contact, allowing us to treat the particles mapping to this node as part of either one side of the crack or the other. So for example, here we see a split for the node in black, where some particles are mapped to field 1 in blue and the rest are mapped to field 2 in orange. But in MPM, we don't explicitly track the evolving crack fronts, and recall that instead we have a diffuse approximation of the crack surface modeled through our damage field. So we additionally need a robust way to detect these cracks. And to do this, we turn to SPH-style kernel methods to define a scalar damage field based on our particle damages. And this allows us to define particle damage gradients, and these gradients in turn give us an idea of where our cracks lie in the material. So ultimately, we can partition our material based on these damage field gradients, and then model the contact between these two fields of particles as separate bodies. So let's take a closer look at how this two-field approach works. So let's start with how we compute particle damage gradients. So we define a scalar damage field D that's spatially weighted using an SPH-style kernel function omega, and we further normalize D to get D bar in order to remove the edge effects by dividing out the kernel sum S. And more intuitively, we show this kernel function below. So for any position in space, we can use this kernel function to weight contributions from all particles within the range RP, which we define based on the MPM grid resolution and problem dimension. And we further normalize query distances using R bar so that our kernel function is simply over the range 0 to 1. And one more thing that our kernel affords us is the ability to dynamically detect material surfaces on the first time step of simulation. And we accomplish this by simply thresholding particle kernel sums based on a user-defined threshold ST. And this works quite well in practice and requires very little additional computation. And more specifically, it robustly gives us a surface representation that can then be treated as damage, enabling us to compute damage gradients that point towards free surfaces. So contact between free surfaces can additionally be treated in the same way that we treat the contact inside of an involving crack. So once we have all of our particle damage gradients, we compute the grid node damage gradients as the highest magnitude particle damage gradient that maps to it. And we can then partition the particles mapping to each node into one of two fields based on the direction of each particle DG in relation to the grid node DG. So let's visualize this a bit. On the left here, we visualize 16 particles colored by their damage, with red being full damage and blue being healthy material. And you can also see their damage gradients each point towards the damage region. And when these 16 particles map to their central grid node colored black, we partition particles with their DG in the same direction as the grid node's DG into one field and the rest into the other field, indicated by the orange and blue colorings of the particle regions on the right. And when we detect that a second field was picked up by the algorithm, we also need to have a heuristic for whether the grid node should be separable or not. And we do this with two metrics. First, by checking that at least one particle mapped to the node had full damage, and the second entails computing a mass-weighted average of particle damage and ensuring it's above some user-defined threshold. And going forward, I'll visualize separable nodes in green. So once we have these separable nodes, we can model frictional contact between the two fields on a separable node using the grid velocities, masses, and normals to evaluate an interpenetration condition, seen here in red. And if the fields are found to be penetrating, we additionally compute and explicitly apply a restorative contact force to each field. And you can see that in yellow here. And at the right, we see that the same slope demo from earlier, we see it with separable nodes in green, but this time we're achieving the sliding we want. And notice that this frictional contact approach allows for controllable interfacial friction, and the block is brought to rest at different points based on this coefficient. So with all that background in mind, let's try and validate this method. So while the authors of this two-field method did validate it through the lens of global fracture, energy dissipation, and fragment sizes, they didn't really perform any explicit tests to validate the underlying fracture mechanics. So of course, if we're going to use this to simulate real-world biological fracture, we need to further validate this method. So first, let's see how this two-field MPM approach works for the scent test. And immediately we see an improvement over single-field MPM. So specifically between 20 and 80% through the crack, we see that the crack is mostly traction-free, save for a bump in the stress concentration factor near the crack opening on the left. And this implies that the opening of the crack is interfering with the overall dynamics of the specimen. And as such, even between 0.2 and 0.8, we still have some residual traction occurring. Fortunately, the spike in traction at the right-hand side is somewhat to be expected since we don't have an explicit representation of where the crack tip actually lies. And this is a detail we can work with since it could instead lead to the interpretation that the crack tip is actually closer to 80% into the defined damage region. However, we did find that we can improve the performance of this two-field approach by being more mindful about mesh resolution. So in this experiment, we enriched the resolution at the crack by explicitly putting a 2dx wide material discontinuity into the specimen. So now we have 2 grid cells worth of particles removed from the specimen where the crack is. And as you can see on the left, the particles at the crack surface are then detected as pink surface particles by two-field MPM and can then be treated as free surfaces in contact. And here on the right side, we visualize the tensile stress field resulting from simulating this specimen with both single-field and two-field MPM. And as you can see, single-field MPM struggles to capture the tension-free crack surfaces, even with this explicit discontinuity. And conversely, two-field looks to be nicely capturing this traction-free surface. More specifically, we can again look at the particle tractions of these 2 specimens, and here we again observe single-field MPM's difficulty with the discontinuity, but even better, we see that we now have a traction-free crack surface modeled by our two-field approach. So clearly, this two-field approach works much better given a little bit of enriched resolution at the crack surface. And now that we've seen that we can model a nearly sharp crack with two-field MPM, let's further see how well this captures a couple other fraction mechanics results for the scent test. So specifically, the second fraction mechanics result we expect to see for the scent specimen comes from analytic relationships from linear elasticity that state that we expect to see a specific power relationship of the stress ahead of the crack tip as we move from the crack tip to the other free surface ahead of the crack. So, and you can see this region is highlighted in the image below here. But more specifically, if we plot the logarithms of our previous metrics, we should see a slope of negative 0.5. And the big takeaway here, as you can see, is that single field MPM fails to produce this slope while two field captures it quite nicely. And our final validation approach we'll look at is also the most rigorous. So we can compute the fracture energy release rate by computing the J integral, a path-independent line integral that circles around the crack tip. And since this integral is entirely path independent, in MPM, our background Cartesian grid gives us a convenient grid-aligned path that we can take around the crack tip to evaluate this expression. So for this final validation approach, we can define the families of contours you see at the bottom left, evaluate the J integrals over time, and compare their average value against an FEM result from commercial software. So here we're plotting for each contour the computed J integral value over time using our two-field MPM approach. And since we're using explicit MPM, we slowly ramp up the traction for the first 4 seconds and then let it oscillate out and come to rest for another 11 seconds. And you can see in the dashed blue line that the average J integral value over time converges very closely to the value we got in FEM, showing yet another successful application of this damage gradient partition two-field MPM. Now, up until this point, we focused on simple mode 1 fracture. So let's see how well two-field MPM handles this more complex shear fracture scenario. So we have here a square plate with an existing crack towards the lower left, and an elastic impactor collides with the lower part of the material to initiate shear crack growth. In the top row, we simulate using damage gradient partition two-field MPM, whereas on the bottom row, we simulate using single-field MPM. And in the left column, we're using a critical stress-based damage model, and in the right column, we're using a new critical stretch-based damage model. So notice how the single field runs on the bottom show an accumulation of damage near the top left of the material where it's held in place by a boundary. And this indicates that the evolved crack path is not properly being modeled as traction-free, and as such, some of the energy that should have gone towards further crack growth instead went into crack growth near that boundary. And you can also see this simply in the way the cracks stop growing before reaching the free surface like they do in the top row. So ultimately, it's pretty clear that DFG partition two-field MPM grants us benefits even for dynamic crack propagation in this complex scenario. So now that we've discussed how we can use two-field MPM to better capture interfacial contact, we can turn to another crucial element in this complex system that we're trying to simulate. And in particular, we also need to model the contact between solid and fluid bodies in our simulation to get accurate stress readings in the blood clot from interactions with the surrounding blood flow. So as we discussed, MPM has a natural ability to couple many materials together into one simulation due to its natural guarantees of non-interpenetration. However, we've seen again and again that this contact is insufficient for modeling the actual interfacial contact forces and friction. So in the next phase of this project, I've been exploring how we can leverage our two-field MPM approach to also capture solid-fluid coupling. And it's quite a simple idea. We're just additionally going to mark grid nodes as separable if they get both solid and fluid particles mapped to them. And as you might expect, we want to physically validate this approach as well. So to validate our solid fluid coupling, we turn to the fluid mechanics of pipe flow and the no slip condition. Basically, this says that after some entrance region, the fluid in a pipe cross section should reach a parabolic velocity profile where the maximal velocity is at the center of the pipe and the viscous fluid in contact with the pipe actually has zero velocity relative to the boundary. So we can design some simple constant pressure pipe flow experiments using a simple viscous fluid model seen here. And the mu parameter here controls viscosity. So let's take a look at some pipe flow examples while varying mu. So here we have an enclosed box of fluid on the left side of a pipe with elastic walls held by Dirichlet boundaries. And there's additionally an enclosed reservoir on the right side to catch the fluid as we push the left wall to force it through the pipe at a constant pressure. And we're coloring the fluid particles by their x velocities. And you can see that in each run, the highest velocity is clearly towards the center of the pipes. But additionally, notice that I've colored the solid fluid contact nodes in cyan here to show where we're modeling the contact, except in the bottom right one where I forgot. So let's look at this a bit more closely. So a good rule of thumb for the entrance region length of a pipe is roughly 10 diameters away from the pipe entrance. So we'll measure the velocities of particles in the small highlighted region here to see the cross-sectional velocity profile for each experiment. So first, let's look at the velocity profile of a pipe simulated without any partitioning, solid fluid coupling, or fluid viscosity. Fitting this data with a quadratic fit has a decent R-squared residual, but you can see that there's some clear inflection of the data that doesn't quite fit the quadratic profile. And conversely, when we add solid fluid coupling, we get a great quadratic fit. And similarly, when we add fluid viscosity, we again get pretty good quadratic fits. However, for higher viscosities like the last two runs with 0.4 and 4, we actually see something closer to a trapezoidal distribution, seeming to indicate that we measured these two while they were still in their entrance regions. And this is actually expected since a more viscous fluid will naturally have a longer entrance region. And this is one of the next things I'll be digging deeper into in this project. But for now, it's exciting that it seems like our two-field solid fluid coupling is allowing us for more to get more or to accurately capture some of these classic effects. So our story ends here for now, but let's overview some of the next challenges I'll be looking at. The first has to do with the inevitable case where a grid node is marked as separable, both from damage gradient partitioning and from solid fluid coupling. And in this case, perhaps a three-field approach could work, but this causes the contact normals to be much less clearly defined, so this easily requires further study. The second challenge is to further validate the accuracy of the shear forces the clot experiences due to blood flow. And these need to be as accurate as possible, or the crack can't possibly evolve accurately. And finally, even though the blood flow should be slightly compressible, unlike water, it's crucial that we don't allow it to compress too much and throw off MPM's particle per cell ratio, which is a crucial part of it working. But in any case, I hope to have more exciting results to share on the horizon, so stay tuned. And here are the acknowledgements of everyone who made these exciting projects possible in my thesis and in my postdoc. So thanks so much for listening. And I've listed here my email and website, as well as our open sourced code for CDMPM and ANISO-MPM. So with that, yeah, thanks again.
Thank you, Joshua. That was an amazing talk. Great job on the pandering, if I may say so myself. You come to Toronto, you use turning red in a slide. So yeah, may I congratulate you on that. I really liked the two talks today, and you're probably listening to me thinking, oh, I like them too. And that's great that you say that, because there's actually a like button below this video that you can click on to let us all know that. And that way our video can reach more people. So if you're watching and you like this, make sure YouTube knows that too. Great, so let's start with our Q&A. I have a lot of questions that I want to get to, so I'm going to just jump to it. Our first questions are for Yifei. So you showed these sort of like very smart numerical tricks by which you can turn the simulation into or make it differentiable and make the backward step feasible, like in memory and time. But when I think of like the challenge that it is to make simulation differentiable, I think of the contact step as like the major like non-differentiable event that happens when you're simulating something. So how do you handle the context? I feel like we might have missed some of it. How does that work?
That's a great question. So indeed, when we're talking about context, we have the context usually has several branches, right? You might have a system that moves from a sliding contact to a sticking contact, and then the shift in the branching statement is non-differentiable, and that is still the case in my work. But we have performed a few experiments where we show we showed even with this I guess non-differentiability in context switching, you can still the gradient information can still be very helpful when you solve this in your task.
And does this, so I guess maybe this is an obvious question, but for those of us that are not used to working in differentiable simulation, is the challenge as hard if you're dealing with sort of self collisions than with collisions with other objects? Are those two similarly handled?
Yes, yeah. So when we talk about discontinuities of context, there are different types of discontinuities. So there's discontinuities in the context set where maybe where say imagine you're optimizing a parameter. If you tweak it just a little bit, the context set changes during the simulation, right? And that's a source of non-differentiability. Right. And yeah, that's a big problem in differentiable simulation. And then for example, in rigid body simulation, differentiable simulation, because of these discontinuities, the gradient might not be as useful. But I think in class simulation, because the simulation has a large degree of freedom, in some sense, the gradient discontinuities can be averaged across all the nodes. So the gradient still globally is still a very useful information when you solve these inverse tasks.
Okay, that makes sense. But I guess another question I have watching your talk was like that example where you had like a ring and you were sort of doing like the goal of getting the cloth through the ring, right? So in that case, the contact is in the loss, so to speak, right? Like your loss is I don't want contacting with the ring. Is that what that's like? And is it using sort of like the same contact formulation as like the contact inside the simulation that you need to detect through the forward and backward paths?
So for that particular task, the ring is actually not modeled in the simulation, but it's just for visualization. So the contact in that simulation mostly comes from self collisions. So when you have arbitrary force field on the class, it can arbitrarily deform, and you have self collisions between the class. So that's where contacts exist in that simulation. In that task, but yeah, there's no between the class and the ring because it's not modeled.
I see. So the ring is more like a position constraint. Like I wanted to go through. Okay, got it.
Yes.
Okay, that makes sense. Thanks. So I have questions for Josh as well. So you at the beginning of your talk, you mentioned MPM as being meshless, which sort of for someone who works in geometry processing is like a great word to hear because it usually means that like, oh, this is not going to be dependent on a discretization. Like this is going to be consistent somehow across discretizations. But you're using a grid in MPM, right? A background grid. So I guess not to enter into like the semantic of whether that is meshless or not, but like how deep is the grid dependency? Because like this, I know that like this is done in fluids a lot using a background grid, but I feel like many of your examples are grid aligned. So like the ones you were showing at the end, you have the pipe's going like straight, like in the grid direction. Is this grid dependency something that you've struggled with or like solved in any way?
Yeah, absolutely. That's a really good point. And even, yeah, calling it a meshless method is almost a little misleading for sure. It's really just that it's a particle-based method. But yeah, the background grid is really acting like a distorted mesh that's evolving over time too. So absolutely, there is like grid resolution has been a problem in NPM, absolutely. And so that's part of why, so for example, in PFF NPM, we want to regularize our diffuse crack approximation based on that grid resolution. So we want our, like where the actual central highest damage part of the crack is going to be within one grid cell, rather than being beyond one grid cell. And so naturally, that's going to be very mesh dependent under certain evolution schemes of phase. But I remember in that paper in CDMPM, we specifically did find that using this phase field evolution with the regularization, it was pretty much mesh invariant, which was awesome to see. Whereas if you used a more local scheme that's just like this particle hits a certain critical stress, market is damaged, that kind of scheme gets you the like extreme mesh dependence. So if you're regularizing, you get around it.
Right. Okay, makes sense. Yeah. I guess that is like a fundamental thing of the method, but if there's a way of regularizing it, then that makes sense. So also at the beginning of the talk, you talked about, and maybe I misheard you, this might be just me, but like you compared and you said like, this is how numerical fracture would look like, and this is how ours would look like. I was struck to hear numerical fracture as something different from what you're doing, which, you know, I guess it's also numerical and it's also fracture. So like, could you maybe reiterate what you mean when you say it's explicitly numerical fracture?
Yeah. So in the earlier fracture approaches that I've used, it really seems like it's actually, so damage is being evolved accurately where it should naturally evolve based on Griffith's like theory of fracture. All of it's like really rigorously derived in terms of like fracture energy, dissipation, and all these things. So the damage is being evolved properly. But I think that what's ultimately happening is that we're just weakening the material enough that it actually is separating far enough that it's then separating numerically. So like the arm of the armadillo is being, the damage is happening where it should, where it tears. And that material is weakened, the stress is lower there, so it's separating more. But that crack is not actually traction free. So there's still some like residual stress along that crack. And ultimately, we're just pulling it hard enough that we just pull past that traction.
Right.
And physically are separating it. So when basically it's that the two parts of the arm are moving, their interpolation stencils are like moving far enough apart that NPM is now like, okay, there's no stress here.
Yeah.
Whereas in the two-field approach, we can more finely actually get that traction-free crack then.
Okay, makes sense. I think I understand the difference. I might bother you offline a little bit more about that. But, okay, so open question: when would you not want to use the material point method?
Oh yeah, lots of times probably. It's definitely not like a panacea at all. So like in animation, they use it for snow and mud. So really, I think like the plasticity based methods are really popular. So like the snow paper from 2013 that was used in Frozen was like totally a plastic snow model. And then I think I think in Frozen 2 they used it for some mud. I swear it looked like NPM. So I think that kind of thing. And I know the water in Moana, they used like APIC NPM for the water. But yeah, there are plenty of times you wouldn't want to use it. And even, I mean, this has been sort of a constant thing. Like, should we just use FEM for this this problem? Because, you know, it has commercial solvers that can do it already. So like for the scent test, for example, like if you want to get a J integral on a scent test, you shouldn't just jump into NPM. Like that's not an easy solution to that problem. It took a lot of engineering to make that work. But when you're getting all of these materials together, that's where FEM starts having more trouble, right? If you want fluid and the clot and another solid elastic thing with a different model, that's where MPM really shines. And of course, huge topology changes FEM kind of struggles with.
Right, just by virtue of a particle-based method. Makes sense.
Exactly.
Okay, so I'll jump to a question for Yifei now. So this is from someone that's very excited about your work, like we all are, who asks, what is the criteria to extend your method to other class models, such as the quadratic bending model, or even other domains of elasticity? Can this be used for differentiable AREP, for example?
Okay, so because our framework is based on the projective dynamics framework, we inherit the limitation from PD, which is the material model has to assume a certain quadratic form. So if the energy or the material model can be written in that form, then our method can easily handle these material models. But if it does not, there needs to be some, I guess, either reformulation of the material model or some, I guess, more work on our diff class end to handle those simulation models.
Okay, makes sense. I guess it depends on the specific model if you can put it in that form or not. Okay, another question for Josh is, okay, you had this. I was a bit disappointed that there were so many examples about ice and things breaking related to ice, and then other things breaking. There was no Titanic. I feel like this should have come to your mind, you know.
Absolutely.
Okay, so since it's not there, I imagine it's because of something. So, and we started to look at all your animations, and they're all like very ductile fractures. So like these are things that you pull and like they bend, and as you pull them, they bend, or like, whereas probably that I wasn't there. But like if the Titanic hits an iceberg, you'll like break into it. There wouldn't be, I assume, very little deformation. It'll just be like a clean break. So is this like a fundamental thing about MPM, or are ductile fractures just most impressive? So those are the ones that you show the videos for?
Yeah, that's probably like the best way to put it, is just, I think it really shines most for the ductile examples. So like we could do the brittle kind of fracture simulation too. And it kind of gets into the question of like, should we be doing this statically or dynamically? Where in the dynamic case, you have like waves of momentum going through the material. And so, for example, that's like a lot harder to do. For example, the J integral, you can't take that when those waves are going on.
Right.
So like, that's a good case where we did the really kind of quasi-static brittle case. But yeah, I think mostly we have like these really ductile cases because it's, really good for extreme deformations and topology change. So we want to like really tear things apart and smash them. And but when you look at the engineering literature, a lot of these phase field MPM fracture approaches are specifically for brittle fracture. So absolutely, because that's probably easier to reason about. Ductile fracture gets complicated because you have like a plastic region at the crack tip. So it's a lot harder to like really rigorously analyze it in the engineering side.
Okay, that makes sense. That was kind of the answer I was hoping for. Okay, so let me end because we're extremely over time. So I'm going to end with an open question to both of you. I think, and this is kind of like the obvious question, but I was watching Yifei's talk and seeing like how there's all these inverse problems that you can phrase in like class simulation. And you can ask, I want a skirt to move this way. What should the design be, or what should the wind be, or the parameters be? I can think of many fracture cases where I would want something like that. So like if you're playing Elden Ring and you want the table to break in this specific way, what does the table design have to be? Or like what does the thing that falls on it has to be so that, within the simulation, it breaks in that way. So I realize that there are like specific points of both your algorithms that would make it, almost impossible to do. Like, your algorithm, as far as I know, is not differentiable, Josh. And obviously there's this like projective dynamics step that you would need to change for something that includes fracture that can't be like specifically plugged into the diff cloth environment. But what are like the fundamental challenges of beyond your two works that make differential fracture difficult, or like what can we expect in the next like 5 years? And I didn't give the question to any one person, so Yifei, why don't you start us off?
I think for inverse problems on fractures, it seems to me that the most difficulty is in the first non-differentiability, and second, you have this inherent discontinuities in fractures where basically if you tweak the parameter a little bit, then you have very different simulation phenomena, meaning the gradient, if you look, meaning if you plot the loss landscape on these parameters, you're going to see many local minimum. And in that case, the gradient might not be very useful. So there will be a lot of work needs to be done, for example, on the optimizer end to jump out of this local minimum. And yeah, that's the first thing that come off of my mind.
Thanks. Yeah, I see. I appreciate that perspective. I don't work in differentiable simulation a lot. So it's great to hear like what the first things that come into your mind are. Josh.
Yeah, that was a really good way to put it, honestly, because as soon as you're tearing something in half, even just one time, the elasticity of that completely changes locally and globally. So I would imagine that that's like a really, really tough problem to fit into something that's so reliant on like smooth gradient spaces, when we have these huge discontinuities that could occur anywhere in the material. Yeah, that kind of problem we did explore when I was doing my PhD. We looked at a lot of like machine learning physical simulation stuff, and we didn't end up pursuing it because I went down this two-field path. But there's a lot of really good work on like machine learning physical simulation work, and a lot of it there are really a lot of difficulties with it in predicting the next step of something, especially at like a really high resolution if you wanted. So yeah, I wouldn't know the first thing about trying to fit this into that schema, honestly.
Well, that's an answer. That's fine. Thank you both. That I think let's end on that hopeful note, and thank you all for coming. Thank you all for watching, and remember to join us next Friday at 11 a.m. Eastern Time to hear from Manuel Oliveira and Sara Socherova. Have a nice weekend, everyone.